Caterpillar owned the ultra-class excavator market, 60 to 70% global share. The 60/60 was the standard everything else was measured against. A family-owned German company nobody had heard of just took it from them. This is how. To understand what Liebherr saw, you have to understand what the mines had become. The deeper you dig, the hotter it gets. Ambient temperatures in Chile's Atacama Desert routinely touch 45 degrees Celsius. In Australia's Pilbara, summer heat pushes past 50. The machines are expected to run 3 shifts a day, every single day, without interruption. That is the baseline. Not ideal conditions, extreme ones. And that is what the machines were being engineered around. The problem was architecture. In Caterpillar's integrated hydraulic system, every function, boom hoist, bucket curl, upper body swing, propel, drew from the same central circuit, one loop, one fluid supply, one thermal load that compounded every time the machine moved. When the fluid heats up, viscosity drops, performance degrades, and then the machine does the one thing a mine operator cannot tolerate. It derates. A 600-ton excavator running at reduced power throws off the entire loading cycle for every haul truck operating alongside it. One machine underperforming ripples outward across dozens of vehicles and hundreds of millions of dollars in annual production. Mine operators knew this. They were living it every summer. Caterpillar knew it too, but solving it within the existing architecture wasn't a tuning problem. It was a structural one, and a company in Germany was paying very close attention. Liebherr's answer was deceptively simple: an independent swing circuit. In a conventional integrated shovel, the upper body's rotational swing competes for pressure with the digging functions. When the machine is simultaneously curling a bucket, hoisting the boom, and beginning a swing, all three are fighting for fluid from the same source. Liebherr separated the swing entirely. In their R9800, the slewing function runs on its own dedicated circuit with its own pump. It doesn't compete with the dig. It doesn't add to the thermal load. It operates in parallel. This sounds modest. The consequences were not. By decoupling swing from digging, Liebherr achieved something Cat's integrated design fundamentally could not: simultaneous full-power operation across multiple functions without accumulating exponential heat. Where Caterpillar used 2 massive pumps feeding one loop, Liebherr built multiple smaller circuits, each optimized for its own task. Think of it like a ship where propulsion, navigation, and life support each have their own independent power source. A failure in one doesn't cascade into the others. Each system operates at its peak without robbing anything else. The practical result was a machine that could curl, hoist, and swing at maximum output simultaneously, without any single function cannibalizing the others. In integrated systems, operators had learned to sequence their inputs to manage the load. With Liebherr, that workaround disappeared. The machine did what operators asked, all of it, at once. The question mine operators were now asking wasn't which machine lifts more. It was which machine keeps lifting when the temperature hits 48 degrees at 2 in the afternoon. The R9800's cooling system is where that question gets answered in the field. The cooling pods are not buried inside the machine's superstructure. They are deliberately oversized and mounted externally, maximizing surface area exposure to ambient airflow. Liebherr engineered in thermal reserve, excess capacity built in intentionally, so that even at peak temperatures the machine is operating well below its cooling limit. It doesn't derate because it was never running close to the edge in the first place. The field data told the story. At peak afternoon temperatures, Caterpillar machines were logging derate events. Liebherr machines were not. Cat's tightly packaged integrated design had less thermal headroom by virtue of its architecture. Engineering that headroom back in without a fundamental rebuild of the machine would have required exactly that, a fundamental rebuild. And rebuilding your flagship product from scratch while actively losing market share is not a position any company wants to be in. But the thermal argument only tells half the story. The other half lives in a metric called MTR, mean time to repair. A 600-ton excavator sitting idle for 8 hours isn't just a maintenance cost. It's a $400,000 productivity loss. In Caterpillar's integrated architecture, a failure anywhere in the main hydraulic loop affects the entire system. Draining and servicing a single component could mean taking the whole circuit offline, sometimes 12 to 20 hours for a repair that on a modular machine takes 3. Liebherr's discrete circuits changed the equation entirely. A failure in the swing circuit doesn't contaminate the main digging loop. Technicians isolate the failed module, remove it, install a pre-built replacement, and return the machine to production without touching the rest of the system. The industry started calling it plug-and-play hydraulics. The MTR numbers coming back from Australian and Chilean operations were not subtle. Liebherr machines were returning to production in hours where competitors were down for days. Across a fleet of 10 excavators running 365 days a year, that difference compounded into thousands of lost production hours annually. In a capital-intensive industry where every idle hour has a precise dollar value, that gap was impossible to argue with. That was the moment the spreadsheet stopped favoring yellow. Markets don't turn overnight. They turn through individual decisions made by procurement managers and engineering directors who read the operating data and run the lifecycle cost models. In the mid-2020s, those models started telling the same story across different mines, different continents, different commodities. Pilbara iron ore operations began placing large-scale orders for Liebherr ultra-class machines, not trial deployments, but full fleet commitments with 15-year asset life cycles. South America followed. The Andean Copper Belt, with its altitude-related thermal challenges and aggressive production targets, became the hardest possible test, and Liebherr passed it. Contracts that had been Caterpillar's almost by default began going to competitive bid, and Liebherr kept winning. For Caterpillar, the problem was structural. The integrated system philosophy was baked into the DNA of the 6000 series. Truly competing would mean designing an entirely new machine from the ground up, a multi-year, multi-billion-dollar commitment with no guarantee of market recovery at the end of it. And the more market share they lost, the harder it became to justify that investment. By the mid-2020s, Caterpillar had quietly scaled back its ultra-class hydraulic shovel ambitions, pivoting instead toward battery electric haul trucks, a segment where their position remained strong. It was a rational decision, but the ultra-class excavator market had shifted, and it was not shifting back. The deeper legacy of this shift isn't market share, it's architectural. The modular design Liebherr built to solve an overheating problem turned out to be exactly the right foundation for the next phase of mining, electrification, and autonomy. Replacing hydraulic functions with electric actuators is dramatically simpler in a machine where each function is already its own discrete circuit. The engineering decisions made to manage heat in the Pilbara became the blueprint for the zero-emission mine of the future. The thermal problem and the electrification opportunity turned out to be the same problem, approached from opposite ends. Caterpillar built the most powerful machine they could. Liebherr asked a different question. What problem is the mine operator actually trying to solve? The answer wasn't lift more tons. It was lift more tons reliably, in the heat without stopping. That reframe, from peak performance to sustained performance, is what changed the world's biggest mines, not through disruption, not through price. Through the insight that in a place where it is 48 degrees and the machine must not stop, the engineer who understands the operator's problem wins, every time.